Have you ever looked at a simple line on a graph and wondered what it's really telling you? Well, today we are going to unlock the story of motion. We're going to see how one little line can reveal an object's entire journey, how fast it's going, if it's speeding up, slowing down, and even when it decides to turn around and go back. Let's jump right in. So here's our game plan. First, we'll get the lay of the land, just decoding the graph itself. Then I'm going to let you in on two really powerful secrets hidden inside these graphs, what the slope of the line means and what the area underneath it tells us. After that, we'll put all our new skills together to read an entire journey from start to finish. And finally, we'll talk about why this is such a crucial tool in the first place. All right, first things first. Before we can start finding all the treasure hidden in these graphs, we've got to understand the map, right? So let's start there, getting comfortable with the basic layout and what exactly we're looking at. I mean, it seems almost too simple, doesn't it? Just one single line? How can it possibly pack in so much information? Think about it. It can show something speeding up, cruising along, slamming on the brakes, and even doing a complete U-turn. That is the power we're about to unpack. Okay, let's break down the axes. You've got time, which is pretty straightforward, just moving forward along the bottom, the horizontal x-axis. But going up the side, the vertical y-axis, that's where we have velocity. And remember, this is super important. Velocity is not just speed. It's a vector, which means it has both speed and direction. And here it is. This is the number one mistake people make, so let's clear it up right now. Do not confuse this with a distance time graph. On this graph, a flat horizontal line does not, I repeat, does not mean the object has stopped. It means it's moving at a steady, constant velocity, zero acceleration. That is a huge difference, and it's key to everything else we're going to talk about. What's really cool is that we can see the object's direction just at a glance. If the line is anywhere above that horizontal axis, its velocity is positive. Let's just call that moving forward. If it dips below the axis, well, its velocity is negative, meaning it's now moving backward. And what if the line is sitting right on the axis? The velocity is zero. The object is actually stopped. And the most dramatic moment? When the line crosses the axis. That is the exact instant it changes direction. Okay, time for our first big secret. The story of how an object's speed is changing, is it flooring it or is it hitting the brakes? That whole story is told by the steepness of the line, or as we call it, the slope. And this makes total sense when you stop and think about it. Back in math class, what was slope? It was the rise over the run, right? The change in the y-axis divided by the change in the x-axis. Well, on our graph, what's that? It's the change in velocity divided by the change in time. And what's the definition of acceleration? The change in velocity over time. It's the exact same thing. So here's how it all plays out visually. If you see a line sloping upwards, that's positive acceleration. The object is speeding up. If you see that flat horizontal line, that's zero acceleration. It's moving at a constant velocity. And if you see a line sloping downwards, that's negative acceleration. It's decelerating or slowing down. It really is that straightforward. Oh, and a quick little side note just for the curious among you, if you ever see a curved line instead of a straight one, don't panic. All that means is that the acceleration isn't constant. The rate of acceleration is actually changing, and that's what makes the line curve. Now, let's get to the second secret. And this one is a truly special feature, kind of like a hidden superpower of these graphs. We've already figured out acceleration by looking at the slope, but what about the total distance the object traveled? For that, we're going to look underneath the line. This is just fantastic. The area that's trapped between the graph line and the x-axis, that gives you the object's displacement. Basically, how far it's moved from where it started. And why does that work? Well, think about it. To find an area, you're essentially multiplying the axes. And what is velocity, say meters per second, multiplied by time in seconds? The seconds cancel out, and you're left with meters, a distance. Pretty cool, right? And calculating this area is way easier than it might sound. All you have to do is break down that space under the line into simple shapes you already know, rectangles, triangles. Then you just find the area of each of those little shapes, add them all up, and boom, you've got the total displacement. Okay, so we have our two secrets. Slope is acceleration and area is displacement. We've got our new superpowers. Now let's combine them and actually read the complete story of a journey, all from a single graph. So let's follow a car's journey. It starts from a dead stop, so its velocity is zero. Then the driver hits the gas. See how the line slopes steadily upward? That's showing a constant positive acceleration. The car is speeding up nice and smooth. Then, let's say the car hits the speed limit on the highway. And look, the line goes totally flat. The slope is 0, which means the acceleration is 0. Now remember, the car isn't stopped. It's just cruising along at a nice, steady, constant speed. All right, now for the last part of this little trip, the line starts to slope back down towards the x-axis. So what's happening here? Take a second, pause if you need to, and think about what that negative slope is telling us. What's the car doing? If you said it's slowing down, you are exactly right. The slope is negative, which just means the acceleration is negative. The car is decelerating, maybe because the driver sees their exit coming up and is preparing to stop. Now for the grand finale. If we were to calculate the total area under that entire 3-part journey, adding up the area of that first triangle, the rectangle in the middle, and the final shape, we'd find the car's total displacement. And for this particular trip, it all adds up to 64 meters. So there you have it. We've decoded the graph, we've uncovered its secrets. Now, let's just quickly wrap up with the most important takeaways. Think of this as your new toolkit for understanding the story of motion. Here it is, everything you need. In one single glance, you now know that a flat line means constant velocity. The steepness, the slope, tells you the acceleration. The area underneath gives you the displacement. If it slopes up, it's speeding up. If it slopes down, it's slowing down. And if it ever crosses that middle axis, it's made a U-turn. With this toolkit, you can decode pretty much any journey. And you know what? Here is one last, beautifully simple way to think about it. Forget positive or negative for a second. Just ask yourself this. Is the line on the graph moving away from the middle x-axis, the 0 velocity line? If it is, the object is speeding up. Is the line moving towards that middle axis? Then it's slowing down. It's as simple as that. So just remember, these graphs are not just for some abstract physics problem. They describe any kind of motion. I mean, think about your commute this morning. You accelerated from your driveway, maybe cruised at a constant speed, then slowed down for traffic. All of that creates a unique shape, a unique story. So I'll just leave you with this thought. What would the velocity time graph of your day